Ma'am, you are not audible.
Yeah, just now audible.
Yes.
Yes, ma'am.
Good evening, everyone. So, how's your quiz?
Good, ma'am.
It was good.
Yes,
Any
ma'am.
technical issues or any doubt in the questions?
No, ma'am. I have no doubt from question.
Okay.
Ma'am,
Yes.
ma'am, I have a doubt. Can you please take it in the last?
Yeah. You have doubt on which in the quiz question or something else?
Ma'am, quiz question, just a small doubt.
Yeah. Yeah. Okay.
Okay.
So start in 5 minutes so that other will join.
Ma'am, you are not audible.
Yeah. Actually, I'm not saying anything. So
Ma'am, is the class started?
no, just 1 minute.
Okay,
Start from.
that's what I'm late. Yeah,
Yeah, Mayank, you can say your doubt. You have doubt on which thing? So in today's class, we just introduce what do you what is the concept of graph theory, some basic things, definition of graphs, vertices, edges, and then we will try to cover the basic process of BFS and DFS. Yes, Mayank, you can tell your doubt. Okay, this thing I don't know, but I'll let you know in sometime after sometime. So let's just start the class. I'll tell you doubt at the end. So graph theory starts with the definition of relations. So you know what do you understand by relation? Relation is nothing but a subset of any Cartesian product A cross A. Suppose you have a set A, and suppose A is my 1, 2, 3, right? Then what do you understand by Cartesian product A cross A? So it is nothing but another set of tuples, suppose x and y, where each x and y belongs to A. So in this case, what is our A cross A? So A cross A is nothing but simply 1, 2, 1, 3, 1, 1 also included, and something like that. And we know that the cardinality of A cross A is just the cardinality of A into cardinality of A. I mean, in general, if you want cardinality of A cross B, it is same as cardinality of A into cardinality of B. Okay. Yeah, this is the first session for week 10. So we'll try to cover up some theory based on the graph and DFS and BFS process. You guys watched some of the videos, or you just started? I mean, just today is just Sunday, so I guess.
Yes, ma'am, we have watched.
Yeah. So first we'll define what do you mean by a graph. So graph G is nothing but a tuple consisting of two things. First thing is set of vertices. It's just a set. You can take any set. I mean, set of, suppose set of numbers, set of people, set of students, anything you can take. But here we try to take the finite set. And the another set is the set of edges. So edges are nothing but simply a way to describe relations between the vertices. Suppose I have this relation that I'll say that A is the father of B. Suppose I have father and son relation, and I have some set. Suppose I have some people, Ram, Sham, whatever, and we can describe a relation in this manner that Ram is a father of Sham, or someone else is. So something, I mean, edges are basically a mathematical way to define a relation between two vertices. So these are called edges, and in mathematics, edges are nothing but the subset of Cartesian product V cross V. You can take any subset of Cartesian product V cross V, and that will form the set of edges, and from that set of edges, you can construct your graph accordingly. For example, suppose this is something that 1, 2, 3, 4, and these are the set of edges. So if this is my G, this is my graph G, this is the visual representation of G. So in mathematical sense, how could you define the graph G? So this graph G consists of the vertex set V as 1, 2, 3, and 4. And the edge set E consists of, now this in this graph, we haven't described the direction on each edge. I mean, we can say that this edge is directed from 4 to 1, or also from 1 to 4. So that's why we divide our graph into two categories. First is the directed graph, in which each edge has a direction, that's known as directed graph, and second one is undirected graph. So that is edges has direction, and the undirected graph, we don't have any direction. So these are the main two distribution of graphs, directed graphs and undirected graph. We'll try to work on the both of the graphs in BFS and DFS also. So here the set of edges, so suppose in this graph I am not assuming any direction. So then the set of edges is just the tuple that 4, 1, 1, 2, and 4, 2, 2, 3, and 1, 3. So this is the mathematical representation of the graph G, and this is the visual representation of graph G. So in two ways we can describe a graph. First is the visual representation, and second is the using the using the what are the elements of edges, and what are the elements of vertices. From that way also we can describe our graph. So this is a
Ma'am,
basic definition. Yes.
ma'am, it won't include 1, 4 in the E.
Oh, sorry. This is the undirected graph, right? So here I don't have any direction. So in this case, 1, 4 and 4, 1 will denote the same thing.
Okay, ma'am.
Yeah. So I'll precisely define what do you mean by directed graph and undirected graph. Okay.
Ma'am,
So let's
you
just
said
start it.
G is a
Yeah.
graph, right?
Yeah.
Sorry, G is a set. So
Yeah. G is
is
a
set
pair of
V.
two sets.
Right. So it would be like this set 1, 2, 3, 4, comma. The
Yeah,
other
that's
set
it.
would be 4, 1 and all that.
Yeah, that's the mathematical representation of graph. In a mathematics, how could you define a graph precisely? Because a picture doesn't make sense to us, right? If I
Right.
simply say that this is my graph, in general, we work with pictures only, but
Right.
to
Mathematics.
derive some properties and all, we need the explicit expression for edges and vertices. That's why.
Oh, okay.
Fine.
Yes, ma'am.
So in general, mathematically, graph is nothing but a pair V comma E with consisting of two sets. V is a set of vertices and E is any subset of V cross V. Any subset of V cross V will form a graph. For example,
Ma'am, is this E set, this vertex set, proper sorry, E set a proper subset or just a
no,
subset?
it could be the whole V cross V also. For example, you take this graph. 1, 2, 3. So this is my set of vertices. V is simply that 1, 2, 3, right? Okay. Now first I'll define what is directed graph and undirected graph. After that it will be clear. Okay. So undirected graph. So undirected graph is basically a graph consisting of set of vertices and set of edges. Here we have constraint on the set of edges that if suppose v1 comma v2 belongs to E, if and only if v2 comma v1 belongs to E. So that means in this undirected graph, we don't need to mention precisely that the tuple v1 comma 2 belongs to E if and only if 2 comma 1 belongs to E. That means in this graph, the direction, we don't have any type of direction here. That's what I was saying. So then we say this is to be an undirected graph. I mean, in undirected graph, it is not basically if I'll say that G is an undirected graph and any edge, suppose 4 comma 5 belongs to E, then it is understandable that 5 comma 4 also belongs to E because we don't have any direction. So this is one thing about undirected graph. And in directed graph, this need not to be the case. This need not to be possible. Right? For example, here I have two graphs. This is my first graph, 1, 2, 3. And similarly, this is a basic difference between directed graph and undirected graph. So here the set of edges is nothing but 1 comma 2, 2 comma 3, 3 comma 1. And it is understandable that okay, 2 comma 1 is also there, 3 comma 2 is also there, and 1 comma 3 is also there. And here the set of edges is precisely 2 comma 1, 1 comma 3, and 3 comma 2. Now you get the difference between directed and undirected graph, right? Directed graph just has direction. The edges has some direction from some vertex to some another vertex. Right?
Right, ma'am.
Okay. So this is one thing, directed graph and undirected graph, edges, vertices. Now, what do you mean by a path in a graph? Okay, so now we precisely, what do you mean by path? I mean, in general, what we mean by a path? Path means that if I want to go from A to some place D, then what are the ways that I can travel, right? So simply first I'll go to A to B and from then B to C and then from C to D. So in our daily life, we say that this is a path from A to D. So similarly in graph also this thing happen. So a path is nothing but a sequence of vertices in which no vertex repeated twice. And if a path started from U to B, so a path from U to V is just a sequence of vertices in between them such that no other vertice is repeated twice. For example, if I'll say that this is my Suppose this is my graph, and I say that I want to travel from this vertex 6 to this vertex 9. Then we can travel in we can travel in different ways. For example, I can go first to 5, then to 2, then to 3, and then to 9. This is one straight path. Now I am calling this path because I am not repeating any vertex in between them. For example, if I started from 6 and then I go to 5, then I go to 7, and then I return to 5, and then I go to 2, and then I go to 3, 2, and then I go to 9. So this is not a path in graph. So a path in graph is simply a sequence of vertices from 6 to 9, which does not repeat any vertex in between them. For example, if the another path you can think about, for example, I'll say I go first I will go to 5, then I'll go to 7, then I'll go to 8, then I'll go to 2, then 3, and then 9. This is again a path, because in this path also we are not repeating any vertex, right? Now you got what do you mean by a path?
Yes, ma'am.
Simply just path means is nothing but a way to go from a vertex u to v without repeating any in between vertex. That's it. Now what do you mean by walk? So walk is nothing a path in which we can repeat our vertex. We can repeat a vertex as well as edge. One thing I want to make here that we never consider these two things. I mean loops. For example, in a graph where I'll say that this is my one edge. So loops are basically not interested that much. So that's why we say that our graph is always loopless. I mean, I won't draw any edge like this, that it started from 4 and ended at 4 itself. So we never consider loops. And second of all, that we never consider multi-edges. What do you mean by multi-edges? Suppose this is my edge from 4 to 3. And if I'll make another edge from 4 to 3, then I don't want this edge because this is useless for me, right? So in our graph, we never consider first thing is loop and second thing is multi-edges. We always try to work with those graph which doesn't have any loops or multi-edges. Multi-edges basically is nothing but an edge whose starting and endpoints are same. For example, this E1 and E2, these two edges are from 5 to 6. So their starting and endpoints are same. So they are called multi-edges. So in our graph, we try to avoid the multi-edges and loops because they are not that much informative for us. Okay. So a walk is nothing but a path in which we can repeat a vertex. For example, here, if I want to walk from 1 to 8, then if I travel through 2 and then 8, then this is again a path plus walk also. And if I want to travel again from 1 to 2, and if I go to 4, then come back to 1, then go to 2, then go to 8, then this is a walk. So basically in a walk, we can repeat a vertex, but in a path, we cannot repeat a vertex. Okay. So this is a walk from the vertex 1 to vertex 8. So walk and path are clear to you?
And ma'am, even if
Excuse
we,
me, ma'am.
Yeah.
Ma'am,
Ma'am, a path can be a walk, but a walk
A walk
not become a path.
need not necessarily be a path. Yeah, that's the thing.
Okay, thank you.
ma'am,
ma'am,
in this graph,
Yeah.
ma'am, that means in walk that vertex can repeat or not repeat.
Yeah. It is possible it could be repeated, it could not be repeated. I mean, it's depend on the walk. How, in which way you want to move, right? For example, if I go to 1 to 2 and then 8, this is also a walk and also a path because here I am not repeating any vertex or edges, right?
Ma'am, if still in a walk, like a series of vertices is a given such that there is a loop inside it, should we still consider it to be a walk?
Uh, Loops. I mean, we never
If it
try.
like
Sorry,
if
what?
it, like if it's given like A B C A B, then further on.
A,
So
B, C, A, B. So yeah, this is a walk because we are repeating the vertex A and B twice. So
A B. So, I
right?
mean,
In
if
this graph, 1,
Yeah.
2, 3, 4, would that be a loop? 1, 2, 3, 4,
1, 2,
1, 1,
3.
2, 3,
No, no,
4,
no.
1.
I will come to that. Loop means which has same vertex. Yeah, okay, fine. No, this is not a loop. Loop is this thing.
Okay,
That an
so it has
edge.
to be on the same vertex.
Yeah. It don't have. I mean, an edge whose starting and ending point is same. This is called the loop.
okay,
Okay.
Loop is basically an edge, not a pair of edges. Okay, an edge whose starting and ending point are same. That we mean by a loop. And multi-edge is, I mean, if there are more than one edges between the vertices, then we say that it is a multi-edge. So we are not consider multi-edges or loop because they are not that much worth it for now time being. Okay. So walk, path are clear. Now we go to cycle.
But multi-edge, sorry, ma'am, I didn't follow
Yeah.
multi-edge.
Multi-edge basically an edge. I mean, suppose this is your two vertex v1 and v2, and you have several edges between them. So
Okay.
these
Okay.
set is called multi-edge.
Okay. Got it.
Yeah. So I mean, we just need one edge. Why do we consider more than one edges, right?
Right.
For example, if you want to build a network in your house, so from one circuit to another circuit, only one wire is sufficient. You don't need to put the separate wires. You're getting my point, right?
Yes, ma'am. Yes.
So that's the multi-edges. Now go to cycle. So what do you mean by
Ma'am,
cycles? Yes.
ma'am, in an unidirectional graph between two vertices,
Yeah.
there could be two um, bidirectional edges. Then there is a possibility of multi-edges.
Yeah. That's why I'm
In this
saying
case.
that we don't consider multi-edges at all. There are possibilities to having a multi-edge, but in our graphs, we don't want to consider multi-edges because they are not that much worth it. So for simplicity, we just consider between any two vertex. If there is an edge, then there is a single edge. We don't want two or more than two edges. Okay.
Ma'am, can I say an unidirectional edge between two vertices is same as having multi-edges with direction
No.
between two vertices?
No, we
It is
cannot say
same.
that because in
But in
directional graph also
undirectional,
we don't worry about multi-edges. We won't consider multi-edge in that scenario also. So I'll come back to that. First, let me go to cycles. Okay, so cycles are basically paths whose starting and endpoints are same. So basically in a path, you move from a vertex U to V. Now, if you move from a vertex U to V, in place of V, if you move from U to U without repeating an edge, without repeating an vertex, then that sequence is called the cycle. For example, in this graph, as you guys says, if we go from 1 to 2, then go to 3, then go to 4, and then come back to 1, this is a cycle because this is simply a path, because we are not repeating a vertex except 1, because 1 is our starting and ending vertex. So a path is nothing. Okay. Yeah, this class is recorded, I guess. Streaming is also. Yeah. So a cycle is nothing but a path in which starting and ending vertex is same. Okay. So that is the cycle. So you guys are okay with this basic terminology? I mean, first edges, vertices, paths, cycles, and walks. These are 5 fundamental things for understanding any graph. Okay. Any doubt?
ma'am, can you repeat cycle again, please?
Cycle is nothing but a path in which your starting vertex and your ending vertex are same. That sequence is called a cycle. For example, here, suppose you consider 5. So first I'll go to I'll start from 5, go to 2, then go to 8, then go to 7, and then return back to 5. So this sequence, that 5 2 8 7 5, this is called a cycle.
Okay.
right? So it is just a path in which your starting and ending vertex are same. So
Ma'am, how is the cycle represented mathematically?
Basically we just represent what are the vertex we are traced. For example, I started from 5, then I basically this type of sequence. If my vertex set is this set 1 2 and so on 9 or 10 in this case, then this sequence is called a cycle mathematically. Just list out what are the vertices you are tracing. That's it. Similarly, path also written in the same way. What are vertices you have been traced in your whole journey? That is called the path.
Ma'am, but then this is looking like a number. No?
Yeah, it's look like a
5
number,
to
but
8, 7, 5.
it looked like a number because I am denoting my vertices using 1 2 3 4. If I denote it from suppose v1 v2 v3, now it won't look like a number, right? It will look like something v1 v5 v2 v8 v7 v5. Suppose I'll denote my vertices the name of cities. Suppose my 5 is my Delhi, Hyderabad, Chennai, Bangalore, something like that. Then your cycle will be written in that way itself, right?
But then how to distinguish between a number and the cycle?
You don't have to worry about that
This
because
is
in a
looking
graph,
like a
in
big
general, we use
number
the
only.
numbers. It's just an information. The vertex could be anything, the cycles could be anything. No one will ask you what are the cycle, write it down explicitly, but you should get a sense that, okay, so in this graph, there is a cycle. That's it. Fine.
I am saying that this is a number, right? Ma'am? 5 to 8, 7.
Yeah, it's a number, but don't
That
look
is
at it
a
as a
number,
number, na?
and the vertex is also denoted by a number. Then how to distinguish between a number? Like if there is
No,
a
no, no. Wait,
uh,
if
two-digit cycle, no? Then how to distinguish whether it is a vertex or
it will
cycle?
explicitly say that given cycle 2 comma 3 or 2 3, I mean they will explicitly say to you, okay, this is a cycle. Or if they say that this is a vertex, then they will explicitly mention that what are the things they are asking. Okay, so
Uh,
you won't get confused.
if it is a cycle, it is represented in a brackets, no?
Yeah, I mean they will mention if they will ask the cycle in terms of the expression, they will precisely
Mhm.
mention that consider this cycle. So whatever the cycles are, then you will work with it.
Okay.
I mean they will write in the wordings itself that consider this cycle. Okay.
Okay.
So now we have another question that in this graph there is a question. So in this graph, if we so if I start with 7, so can I go to any other vertex? So via path.
Yes, ma'am.
Yes, obviously you can go because every vertex has a path from 7. So these type of questions are interested. These type of questions are known as reachability question. That means we can move from a vertex. So that means can we are able to move from a vertex in a graph to another vertex in the precise graph in that graph itself. So this is a called reachability question. So the precise definition is that a vertex U is reachable from another vertex V in a graph G if and only if there is a path there is a path between U and V. So this is known as reachability question. That basic thing is that, so can we move from a one place to another place? That's type of question. For example, in this graph, suppose this is your graph. It's 1, 2, 3, 4, and 3, and this is 4. This whole picture is your graph. So in this picture, you know that I mean you're observing that we cannot reach 4 from any of the other vertices, right? Because there is no edge between them. So that means 4 is not reachable from any other vertices. So in a complicated graph also, our goal is to find out those vertices which are reachable from every other vertices, or those vertices which are not reachable from other vertices. Okay. So you understand what does reachability term means, right?
Ma'am, should not we say that it's a path from U to V?
Yeah. Basically, if there is a path from U to V, we say that, okay, we can go from U to V or V to U. That's the thing. In an undirected graph, if there is no direction, then only. In a directed graph, reachability has two sense. Okay. So let's come to directed graph. So in directed graph, when we consider path, we also consider the directions of edges also. I mean, we take care of the direction of edges. For example, if this is my path, then there is no way for reaching 1 to 2. 1 to 2, there is no path. Because we can move from 1 to 3, but again from 3 to 2, there is no edge. If I make this edge in this way, that it has both, I mean, we can move in both of the direction, then we can move from 3 to 2. But if there is no such a sign, then there is no path between 1 to 2. So in directed graph, when we consider path, we also consider what are the directions of the edges. Okay.
Okay, in
Simple.
that case, when we say that visibility in the directed graph, then it will be mentioned in the context from which vertex we are going to which vertex.
Yeah. So that means in a directed graph, it is possible you can go from U to V, but cannot come back from V to U. It is possible in a directed graph, but in an undirected graph, if we find a path between U to V, then we can obviously find a path from V to U, because there is no direction constraint, right? We can just trace that path back. But in a directed graph, we also take care of what are the directions of our edges. Then only we can move from one vertex to another vertex. So again, the path in a directed graph is basically simply a path, but also we have to take care of the directions of edges. Okay. And simple, a cycle and also a directed graph is basically a cycle, and we also have to take care what are the directions of the edges. For example, here we don't have any cycle, right? Because we cannot travel from 1 to 3 and then 3 to 2 and then 2 to 1. We can go from 2 to 1 and 1 to 3, but again we cannot go from 3 to 2, right? So for example, this is a cycle in a graph, in a directed graph. So now I can move from 3 to 1, then 1 to 2, and then 2 to 3. So this is a cycle in a directed graph. So in a directed graph, everything, whatever we describe in an undirected graph. So plus point is that we just have to take care of the directions of edges, nothing else. Okay. Got
Ma'am,
it? Yes.
ma'am, if there is no arrow between the two edges, two vertices, then it will be considered as undirected or no path.
It won't happen that some edges has the direction, some edges doesn't have a direction, because we typically want to describe into two different paths. If it is undirected, it will be fully undirected, or if it is directed, it will be fully directed. Okay, so that's the one thing. Or in some textbooks, they won't use this type of edges. That suppose here I have used that 3 and 2 are also related, right? So I'm using this notation to define that, okay, this edge has both of the direction, right?
Yes, ma'am.
So some textbooks just write it in the simpler way. So if you find out that there are some directions, I mean some edges which has direction, and there are one or two edges which is just simply right in this way. So you assume this edge that it has both direction. I mean we can travel from both of the direction, from left to right, also from right to left. Okay, so don't get confused. Fine.
Yes, ma'am. Generally, the undirected graph don't have any arrows.
Yeah. So some textbooks write this type of edges in the directed graph, and some textbooks just write down a simple line between them two vertices to say that, okay, you can move in any direction using that edge.
Okay, ma'am.
So this is the directed graph and undirected graph. reachability. Now we have connectedness. So we say our graph G is connected if there is a path between any two vertices. If you are able to find a path between any two vertices of a graph, then we say that our graph is connected. So it's simple definition, right? Okay. For example, suppose this graph. I'm not labeling the vertices. So does this graph is connected or not?
Yes, ma'am, it's connected.
Yes,
Yeah, it is connected, right? Because we can easily move from any vertex to any other vertex. We can easily find a path. Suppose this is my vertex 1, this is my vertex 5, or any number you can take. So I can move, I want to find a path between the vertex 1 and 5. So what we will do? So we can travel to this vertex and then travel to this vertex. So we always, we can always find a path between any two vertex. Then that graph is called the connected graph. Now, now observe this graph. Okay. Suppose this is my graph G. Now this graph is connected or disconnected?
it's disconnected, ma'am.
Yeah, it is disconnected because basically you can find any path between, you can reach any vertex in this component, and you can reach any vertex in this component, but there is no way from going this component to this component, right? We cannot reach, we cannot connect these two vertex. There is no path between this vertex U and V. So that's why this graph is disconnected. Okay. So now here you observe that, okay, in a graph, we have some connected components. This is a one connected component. So that means a disconnected graph can be described as a union of connected components, right? So we can collect all the connected components of a graph and we can describe it G to be disconnected graph. So in a disconnected graph, we have a connected components more than one, right? So if G is disconnected, then number of connected components. Connected component basically means that what are the parts of a graph which are itself connected. For example, in this part, I can find a way from moving one vertex to any other vertex in this component, right? So if G is your disconnected graph, then the number of connected components are strictly greater than one. So this is one thing. So now we go to coloring problem. So in many fields, we want to we want to give, suppose I have to conduct a session in a day. So I'll try to manage such any type of schedule so that my classes won't clash, right? So for such problems, or for you can say that spreading a business, if you want to spread a business and you want to select some cities which are easier to travel, then for solving such type of questions, this coloring concept are very useful. For example, in this coloring, what you have to do, you have to color the vertices of a graph in such a way, no two adjacent vertices. What do you mean by adjacent vertices? If there is an edge between any two vertex, if there is a single edge between any two vertex U and V, I say that these two vertices are adjacent. This is mean by adjacent vertices. Adjacents with just neighbor of each other. If there is an edge between two vertices, we say that these two vertices are adjacent. Okay. So coloring of a graph is basically mean that we have to color we have to color the vertices of a graph in such a way that no two adjacent vertices have a same color. right? So so if I want to color a graph, then by coloring a graph, I mean I want to give I want to assign each vertex a color in such a way that if there is an adjacent vertex to that vertex should not take the same color as we colored the before vertex. So in mathematical sense, coloring is denoted by simply a function c from a vertex set V, because I want to assign each color to a vertex, okay, from a vertex set V to a set of colors, suppose C of V. This is a set of colors, right? So basically a function from set of vertices to set of colors is known as the coloring of a graph. Coloring of, okay. For example, if you have this type of graph, this is my V1, V2, V3, V4, and these are the edges. Now, if I want to color this graph, then what are the possible way? I mean, since V1 and V2 are not adjacent, I can give any color. I mean, I can give this as a red color and this also red as a red color, right? Because they are these, I mean, V1 and V2 are not adjacent to each other, so I can use the same color. But I cannot give V4 to be the red color because my V1 and V4 are adjacent because there is an edge between V1 and V4. So I cannot use the red color for coloring this graph. So I'll use some another color. Let us suppose that blue. And similarly, this V1 and V3 are adjacent to each other. So we cannot take the red color to V3, but I can take the blue color because V4 and V3 is not adjacent, right? So I can assign a blue color here. So this is one type of coloring to this graph. So basically coloring means nothing. I want to assign each vertex a color in such a way that the neighboring vertex or the adjacent vertex won't get the same color. This is what do you mean by coloring, right? Got it?
Yes, ma'am.
Yeah. So our goal is to find, so this is what do we mean by coloring. So what is our goal? So our goal is to find the minimum number of color. Find the minimum number of color for coloring any graph. So that's our main problem, that find a minimum number of colors so that we can color our whole graph using that minimum number of colors. Okay, for example, here I have used only 2 colors to color this graph. I also can use 4 colors. For example, I'll say V1 will get red color, V2 will get some another color, suppose orange or something, V3 get some black, right? So here, so now this is also one type of coloring of this graph, but here I'm using 4 colors, right? So our main goal is to find out the number of colors which from what we can color the whole graph using this adjacency relation. That means any 2 vertex which are adjacent won't get the same color. Okay, so that's our main goal, and that type of question you can, I mean, you can see in your assignments also, that how many colors are, what are the minimum number of colors for coloring a particular graph. For example, suppose this is my graph. V1, V2. Right. So then what is the minimum number of color?
2, ma'am.
Yeah, correct, 2, right? Everyone is fine with this, that we just need 2 colors to color this graph. You can assign a color here, but then same color you cannot use for these 4 vertices because they are adjacent. So you can take any other color. For suppose I'll take blue here and I'll take red to all others. So this is the basic notion of coloring. And what is our goal in the coloring? That I have to find the minimum number of colors for coloring the whole graph, right? Okay.
But ma'am, mathematically, how do we find, if we don't have a graph, how do we find the minimum this thing?
Yeah,
By
actually,
graph, we can easily look and say that, yeah, okay, 2. But when it
yeah,
gets very complicated, there has to be
yeah.
some
Yeah, so
mathematics.
for now you don't have to worry about that because it is actually very complicated. I mean, this coloring, so many research have done based on this coloring problem. Okay, so for your purpose, we will just give you the graph itself or the picture of graph itself. Then you have to define that what is the minimal possible coloring. We don't give the abstract notion of graph or set of vertices, set of edges itself. We just give you to the picture, and then from that picture you have to observe that what are the minimum possible colors we can use to color this graph. Okay.
Ma'am,
Yes.
in this graph that V2, V3 and V4 and V5 are not adjacent. That's why we can give a single color to them.
Yeah, that's why we can use the similar color. If they will adjacent, then we cannot use the similar color.
Yes, ma'am.
Because that's the first constraint we have applied when we say that if we want to color a graph in such a way. Because if we can suppose if we can do any, I mean, if I remove this constraint, then there is no mean of coloring, right? You can do anything, but because of that constraint only, we can able to find that what is the minimum possible number of colors to color a graph, right?
Yes, ma'am.
So in examples, I mean, in questions also, you have given a precise diagram of a graph, and then we say that to find out what are the possible minimum number of coloring to color a graph. So one of the famous example is this type of graph. Suppose this is your vertex. This is some another vertex. Suppose this is your graph. So in this graph, what is the possible, I mean, what is the minimum number of colors? Minimum number of colors to color this graph.
Again, 2.
No, 2 is not the correct answer. Just observe a little bit, because there are edges between these vertices also.
3.
Yeah. So we can color this graph using 3 colors. How?
No, one for the center, or like
Yeah,
if we
correct.
take
One for the center, and
now and up or rest of the edges and alternate colors of 2.
yeah, correct. Rest of the vertices we can color it using the alternate colors. That will work for us, right? So these type of question you may suppose in the practice assignment or in any other things. Okay. So because these are the basic questions for coloring. That's it, right? So we have, I mean, we cannot color this graph using 2 colors, right? Because if I use one color for the center, then I just remain with a one color, right? So we cannot cover the whole thing using the 2 colors. I need at least 3 colors, right? At least 3 colors required for coloring the whole graph. Okay. Any doubt?
Ma'am,
Yes.
can you just scroll up
Yeah.
the previous graph for coloring? Not this one, the first one.
This one?
Yeah, this one. Here, V2 and V3 are not related, right? But
No, they
then
are
how
adjacent by
can we
this
say
edge.
about their no, V2 and V3?
V2 and V3 are not adjacent. Yeah, right. We can take any color for V2. It doesn't matter, because V2 is not connected to any of the vertex. So
If okay, if two vertices are not related, then uh,
yeah, you can use
we
the same
can't say
color for
about
both of
the
them.
adjacency.
Yeah, if 2 vertices are not adjacent, you can use the same color for both of the vertices. So that's so now we go for the main topic, adjacency matrices. Text. So now, as usual, for a graph G, we try to assign a matrix related to the graph G. Okay. So how will you construct a matrix related to a particular graph G? Okay. So you have given a graph G. So that means you have given a set of vertices and you have given the set of edges. Okay. So suppose I have n number of vertices, 1, 2, up to n. So then I have to construct a matrix. So what I'll do, so I'll form a n by n, what you say, n by n grid, in which I'll say that this is my column for vertex 1, 2, 3, and so on. and again 1, 2, 3, and so on, right? Okay, so the now I have here n square box, right? So that means this could be expressed as an n cross n matrix. You guys are familiar with matrix, right? Matrix is nothing but a collection of entries. For example, here I have to fill n square entries. So I'll fill in this such a manner that I say that the box or the entry Aij, where Aij is the address. This is the, what can you say? This is a box in ith row and jth column. So I say that my this box Aij is equals to 1 if there is an edge between I and j. Because I and j is my vertices, right? Because I am denoting my vertices using the numbers. So I say that this box I and j is equals to 1 if there is an edge between I and j, the vertex I and vertex j. And this entry is equals to 0 if there does not exist any edge between I to j. Right? So in this manner, I can form a matrix related to a graph G. Okay. So I'll give an example so that will be more clear. For example, this example itself. Okay. So here I have 10 vertices. So, and I have to construct a matrix using for this graph. Okay. So that means what I have to do, I have to construct a 10 cross 10 matrix because I have 10 vertices. So I'll list it out 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And similarly here also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right. Now this is my first box. Okay. So this first entry will be 1 if there is an edge between 1 and 1. But in a graph, we never consider loops, right? So this entry will be 0 because there is no edge between 1 and 1. You guys got it?
Yes.
Yeah. So again, let's move for the second box. So this box, this box, we have an edge between 1 and 2. So that's why this box, the entry in this box is 1, right? Because I say that my Aij, that the entry in the ijth box means this is a box at ith row and jth column. So it is 1 if there is an edge between I and j. And it is 0 if there does not exist any edge between I and j. So precisely here between 1 and 2 there is an edge. So that's why I'm writing it 1. Okay. Now from again 1 and 3 there we don't have any edge. So write it 0. Again from 1 and 4 we have an edge. So we'll write it 1. Okay. Again 1 and 5 we don't have any direct edge. Right. So we'll write it 0. I want a single edge between two vertices. Then only I will write 1 into that box. Otherwise I will write it 0. Okay. Similarly, 1 and 6, we don't have edge, so 0. Again, here we have 0, 0, 0, 0, right? So this is the first row of our matrix. Now you guys got it? How we construct the adjacency matrix to a related to a graph.
Yes,
right? Yeah. So I'll just fill up 1 or 2 entries more. So suppose I want to fill this row. So what I'll do, so I'll observe that is there any row between 4 and 1? So answer is yes. So I'll write it 1. There is row between 4 and 2. So no, so 0. Again 4 and 3 we have a row. So that's why it is 1. 4 and 4 we don't have a row. So we'll put it 0. 4 and 5 again we don't have any row because the only neighbors of 4 are 1 and 3. So that's why the only entries are 1 are in the column 1 and in the column 3. Okay. So in this manner, we can fill out the whole matrix, and this matrix is known as the adjacency matrix for a graph G. Okay. This is process for undirected graph. For directed graph, we have slightly different notion. I mean, it is just same thing that we have to fill our matrix by observing what are the vertices connected to other vertices. But again, we have to deal with the directions. So this is for undirected graphs. Now for directed graph, This is just the same thing that we say that our Aij box contain the value 1 if there is an edge between from I to j. I mean, I want this direction edge, not the other way around. Then I'll put it 1, otherwise I will put it 0. 0 if there does not exist any edge from I to j. For example, if I'll give this graph a direction, suppose this is my direction. Now this is my directed graph. Okay. So in this directed graph, if I want to construct the adjacency matrix, so I'll process in the same manner. First, I'll look if there is an edge from 1 to 1. So no, there is no edge from 1 to 1, so I put it 0. So is there is an edge from 1 to 2? So answer is yes, because I have an edge which is coming from 1 and visiting 2, right? So this is my entry. This entry will be 1. Now there is an edge from 1 to 3, so answer is no. There is an edge from 1 to which started at 1 and ended at 4, so answer is yes, so it will be 1. And again the other entries will be 0. Right, so this is one thing. Suppose I want to fill the entries regarding to the number 3. Okay. So there is no edge from 3 to 1, so I'll put it 0. Now again there is no edge from 3 to 2, so I'll put it. There is an edge from 2 to 3, not in from 3 to 2. So that's why this entry will be 0, right? Right?
Yeah. Right.
Again, there is no edge between 3 to 3, so it's also 0. Now again, there is an edge between 4 to 3, not from 3 to 4. I want 3 to 4, not 4 to 3. So that's why it is also 0. And all other entries will also 0. Again, there is an edge between 3 to 9, but not, there is an edge between 9 to 3, but not from 3 to 9. So that's why this entry will be 0. So observe there, this whole row will become 0. So that's the slight difference between directed graph adjacency matrix and undirected graph adjacency matrix. Okay, here you just have to take care of these directions. That if there is an edge between I to j, then I'll put 1. Otherwise, I'll put 0. Okay. So got it?
Tail will always be on the row, not on the columns, right?
Sorry, what?
No, tail of the arrow, tail of this arrow, tail and head, right? So it always be on the row, your tail, and arrow head will be on the columns.
Yeah, correct.
It cannot be other way around. Okay.
No, cannot be another way. I mean, this is the general acceptance. In exam, you won't find out these numberings there. You just have purely metrics. From there only you have to judge it. Okay. So it is it is general understanding that we are using rows to represent the directions. That if there is a row, if there is an edge between this entry and this entry, then I'll put it 1, otherwise 0. So yeah, this is a general as.
Thank you.
Ma'am, and in an
Yes.
adjacency matrix, the number of rows and the number of columns are equal.
Yeah, because we are using vertices itself to define, to what you can say, relate to the number of rows and number of columns. So it's always a square matrix.
So the other name for the square matrix is adjacency matrix. You can say that.
Sorry, what?
Ma'am, the characteristic feature of the adjacency matrix is that the number of the rows will be equal to the number of the columns.
Yeah.
We can say
Every
that.
adjacency matrix should be square matrix, because we are denoting the columns also by the same entries. If there are n vertices, then it will be an n cross n matrix. So yeah, in some sense you can say. Now there is one characterization about adjacency matrix of the undirected graph. Okay. So as you observe that in undirected graph, if we have an edge between I to j, then we also have an edge between j to I, because we don't have to consider the the direction, right? So in that case, your adjacency matrix will always be symmetric. You know what do you mean by symmetric matrix, right?
Yeah.
Symmetric matrix means it is what are the entries are appearing this side, the opposite of the diagonal are same as this side. In general mathematics, we say that Aij is equals to Aj, where Aij is the ijth entry of a matrix. So the adjacency matrix related to an undirected graph is always a symmetric matrix. Okay. And the diagonal entries of adjacency matrix are always zero because we never consider the loops, right? So that's the thing, that the diagonal entry of every adjacency matrix are always zero. And the adjacency matrix related to undirected graph are always symmetrics. So using this thing, you can judge the, observing the matrix, you can judge your graph that it is what you can say, directed or undirected. Okay. If it is symmetric, it should be undirected. And if it is not symmetric, so that means there is an edge which is going from I to J, but not coming back from J to I, right? Okay. So any doubt in this thing, adjacency matrix? No? Okay. So now, what do you call a neighbor? Now second notion is adjacency list. So in adjacency list is basically a list of vertices in such a way. In place of matrix, we just use a list to observe the graph. Here we have vertices, and here we have adjacent vertices. For example, in this graph, okay, so in this graph, you observe that if the vertex is 1, then their adjacent vertex are just 4 and 2, because 4 and 2 adjacent vertex means if there is an edge between that vertex to another vertex, that vertex is called the adjacent. Adjacent simply you can assume to be a neighbor of that vertex, right? Okay. So 4 and 2 are the neighbors of 1. So this is one thing, and adjacent to 2 is 1, 3, 5, 8, and what are the other things? 7, right? Yeah. So in this way, you will form a list, and that list is known as adjacency list. Okay. So adjacency list is basically nothing but in one part you write the vertices, in the other part you write what are the adjacency vertices to that vertices, is known as adjacency list. So these are two notions for understanding a graph. First is adjacency matrices, and second is adjacency list. Okay. So that's one thing. Now we go to independence and dependence of vertex. Okay. So in a graph G, suppose I have a set I which contains some vertices, suppose V1, V2, and so on, Vj, any subset of a vertex set V. So we say that this set is independent set if any if all the VIs are non-adjacent to each other. So that means a subset of a vertex set in which we cannot find an edge between any two vertex. This is known as the independent set of a vertex set. Okay. So this independent set is also an important notion. So try to understand what do you mean by independent set. Basically, we just collect all those vertices which do not share an edge between them, right? Okay. For example, in our graph, if I say that your I is basically 1, 8, 10, and 9. So does this set is independent set or not?
Yes.
Does I is independent? Right, it is
Yes,
independent
yes.
because you can observe that there is no edge between any of the vertex. There is no edge between 1 and 8, there is no edge between 1 and 10, 1 and 9, similarly 8 and 10, 8 and 9, right? And 9 and 10. There is no edge between any of them, direct edge, right?
Yeah.
So that's why it is an independent set. So basically, independent set is a subset of a vertex set in which each Vi and each Vj are non-adjacent. Non-adjacent means there is no direct edge between any of the two vertices. So that set is known as independent set. For example, if I will consider 1, 8, 5, 10, then this set is independent or not?
No.
No.
No, right? Because there is an edge, there is a direct edge between 5 and 8.
Yeah.
Right? So that's why this set is not independent. So not independence is basically say that dependent set. Right? So if there is an edge between any two vertices, that set will be dependent, otherwise it will be independent. Okay. So this is known as an independent set. Now we have to go with the set vertex cover.
If in the set even for one edge exists, then we will consider it as an a dependent.
Yeah. If it is one, I mean at least one, I can say that at least two vertices are adjacent to each other. So that means there is a one edge between any two vertices.
Okay.
At least one. It is possible. For example, if I'll say that this set 2, 5, 7, 8, right? In this set, every vertex is connected to every other vertex by a single edge, right? Because there is an edge between 2 and 5, 5 and 7, 7 and 8, 8 and 5, right? So this
Yes.
set is also a dependent set.
Okay.
Yeah. So not precisely a single edge, it could be more than one edges. I mean, it could be more than two vertices which are not adjacent to each other. Okay. Now the next definition is vertex cover. So these are basically, basic definitions of graph theory. So using these definitions, I'll define some other things, but you should understand what are the meaning of the definition. That's it. What do you mean by independent set, vertex cover, adjacency matrices, adjacency list? That's all. Okay. So again, vertex cover is suppose vertex cover is basically again E. I can denote it. So suppose C is any subset of V. V is our vertex set, right? So we say that this C is a vertex cover if all the edges of a graph G has at least one endpoint in vertex in C. So that means vertex cover is basically selecting such type of vertex which will cover the whole graph. Right, so its name is vertex cover. So that means I have to select such vertex from a graph which will cover the whole graph, in the sense that let me give an example. So in our graph, if I'll select this 2 as in my vertex set, in my vertex cover, suppose this is my C, I'll select 2. Okay, so if I'll select 2, then this edge, this edge, this edge, this edge, and this edge, these 3 edge has an endpoint which is 2, right? So these all 5 edges have been covered using the single vertex 2. So now if I select 5, then again this edge, this edge, this edge will be covered by 5. Similarly, I have to select 7, then these 3 edges also covered by 7. Then I'll select 8, then these 2 edges also covered by our thing. Then I'll select 4. So 4 will take care of these 2 edges. Then I'll select 3, then 3 will take care of these 2 edges. So I get my C to be this set, that 2, 5, 7, 8, 4, and 3, right? And it is a
Ma'am, why
subset
do we
of,
need 8? Why do we need 8, ma'am?
I mean, if I
What?
want to select, we don't need it, right? Because I have considered 2, 5, and 7 itself, so we don't need
Right.
it, right? So, but if you consider 8 itself, now that's, that will also an vertex cover, right?
Ma'am, 7 is also not required. Right? I'm considering 5.
Yeah, that's okay. I mean, 7 also not required, so that will
No,
become
7 is
minimum.
required because 7 is required
Between
because
7 to
7 and
8.
8
Yeah.
cannot be coupled.
If I'll not consider 8, then one of them will be required. Either 8 is required or 7 is required, right? Because in a cycle we don't need to consider
But there is an edge from 5 to 8 now.
But
but
7 to
There
8
is
we
an
if I
have to
won't,
take.
edge from 5 to 8.
right, if I won't take 8, then this edge won't be considered. If I won't take 8 and 7, both of them, suppose I will remove 8 and remove 7, then this edge won't be covered by our vertex cover, right?
Yeah.
Yeah, so that's why.
Means
So
for the vertex cover, all the edges should be covered
yeah, so vertex cover
for the
basically a
vertexes.
subset of your vertex set such that all the edges should be covered. Okay, so now what you guys are thinking that we are constructing the
Okay.
minimum vertex cover. It is not always the case. I mean, vertex cover could be any subset which cover all the edges. It is possible that it will two vertex will cover the same edge. For example, if I'll consider this C1, C1 will be my whatever we are making 2, 5, 7. I'll suppose I'll take 7 and 8 both, right? 4, 3. Then this set is also cover all the edges, right?
Yeah.
Yeah. And suppose I'll remove one of them. Then this set is also cover all the edges. Right? So that means they both qualify for vertex cover. We say that our C1 and C2 both are vertex cover. So vertex cover is, and itself, if you consider V itself, suppose I'll consider V to be my C3. I mean, I'll take all the vertices. Then that is also a vertex cover for a graph. So basically, vertex cover is just collecting those vertices which will take care of all the edges adjacent to that, right? Now getting the feel, what do you mean by vertex cover, right?
Yeah. It is like CCTV camera on road.
Yeah, correct. Something like that you can assume. So basically, vertex cover means just try to find out all the points which will take care of all other the edges. So that's the notion of vertex cover. Okay. So independent set,
Ma'am,
but yeah,
ma'am, can you take in one more example, please, ma'am, for the vertex cover?
vertex cover example. Okay, fine. For example, just take simple thing. You have this set, and then you have this thing. Now just tell me what is the one possible vertex cover. Okay, so I'll denote it by one, suppose A, B, C, D, E, F. Okay, now tell me what is the vertex cover. Any vertex cover, start with anything and just, okay, just answer in the chat box.
The easiest would be, ma'am, all points, all vertices, right?
Yeah, the easiest will be all vertices, right? Because if you take all vertices, obviously all edges will come, right? The easiest thing will be all vertex. That's why in vertex cover, our main goal is to find what is the, for coloring. In the case of coloring, you also take the n different colors to color a graph, right? That's also possible, right? So there also we want to find what is the minimum number of colors. Similarly, here also we want to find what is the minimum number of vertices to cover a graph. That will call the minimum vertex cover. But for time being, just tell me one vertex cover you are able to think. Okay.
BCE.
Yeah, B, C, E. But then this edge won't be covered now.
Then F
Between
also.
D and F. Yeah.
Yeah.
And between B,
E, C, E, F.
B, C, and A. Yeah, A is also required.
Yeah, that's correct.
Ma'am, A, C, then
A, C. Then this edge will covered. This edge also covered. This will edge. This also covered. Then you have to take two of them, right? E, F. If you have to take two of them. Between three, you have to take at least two, right? E and F. Suppose you take, I mean, A, C, D. Okay, I'll take D and E. This will be our vertex cover, right?
Yeah, right.
Yeah. So that's a vertex cover. Vertex cover is basically a collection of vertices from which we can able to try the cover the whole graph. Okay. So here our main motto is to find the minimum vertex cover, a size of minimum vertex cover mainly. Okay. Again, there is no general method to find the size of minimum vertex cover. First is by observing that you can observe, just try to think that, okay, so it cannot be covered by three vertices. So I have to go one more and one more. So this is a one way to get a vertex cover. Okay. So let's go to next one. So everyone is fine with vertex cover? Any doubt? No.
Ma'am, in this case, minimum vertex cover is not different, right?
In this case, minimum. So what happened now? Here we have a cycle, right? A, B, C. Here we have a cycle. Whenever we have a cycle, we have to take two vertices, because then only we are able to cover three edges. So from this thing, I have to take two vertices. From this thing also, I have to take two vertices. So the minimum vertex cover will be size of 4. I mean, we cannot cover this graph less than 4 vertex. You can check it that we cannot, we are not, I mean, the size of minimum vertex cover for this graph is 3. Sorry, 4. You cannot able to cover this whole graph using 3 vertices. You can able, I mean, you can check it. There always be an edge which will not cover using that set. Okay. For now, just
Then the
understand
order
what.
doesn't matter. No?
Sorry, what?
The minimum could be B, C, D, E, or
Yeah,
A,
it
B,
it
D,
need not
A,
to be
or
unique. Yeah,
F,
obviously
G,
it
D.
need not to be unique, but the cardinality should be unique, right? I mean, that's why we are mainly focused on the size of minimum vertex
Mhm.
cover, because it could be different, but the size will be same.
Size of the minimum is defined.
Yeah.
Ma'am, it could be A, B, D, and E also, na?
Yeah, it could be anything. You can choose whatever you want to choose. You don't have even though select A. Okay, just take C, B, E, F. This is also a minimum vertex cover. But main thing is that this also has 4 elements, right? So size is important here. Size of a minimum vertex cover. That's why we are precisely emphasizing on size. That size is important. Yeah, I'll come to matching it. Okay. So this is a one top. I mean, this is a one concept, that vertex cover. Okay. Now we go to second one. Second one is called matching. Matching in a graph G. So matching is basically, as you see, the vertex cover is a subset of vertex set, and matching is a subset of edge set E, such that no two edges of M will share a vertex. I mean, matching is basically collecting all those edges which have different endpoints. That is called the matching. Okay. For example, you have this graph. So if I'll take this edge E1 and this edge E2 and this edge E3, and I'll form my set M to be E1, E2, E3, right? Then these three edges are not sharing any vertex, right? Because E2 has endpoints 5 and 8, E3 has endpoints 3 and 10, and E1 has endpoint 4 and 1. So they both are not sharing any vertex. So that type of subset of an edge set is called a matching. So then this M is called a matching, right? So matching is basically subset of an edge set in which every edge should not share a common vertex, right? Collect those edges which are not share a common vertex. For example, if I'll consider this set, E1, E2, E3, E4, E5, E6, E7, E8, 9. Okay, suppose I'll take E9, E3, E6, E1. Does it a matching? Does this set is a matching?
No,
No, right?
Uh,
Because
ma'am,
because it's sharing the three vertex.
yeah, correct,
ma'am,
correct. I mean,
could you repeat this
E3
matching?
and E6 have a common endpoint, which is 3. I mean, they share a common vertex, right? So in a matching, every edge should not share I mean, any two edge should not share a common vertex. Here, our E6 and E3 are sharing this vertex 3, right? So that's why this set is not a matching. So basically, matching is nothing, but you collect those edges from your edge set which are not sharing the vertices. That's all called. That's called the matching. Okay, got it?
Yeah.
The matching is clear to everyone? Okay, fine. Now there is a notion.
Ma'am, could you repeat again the matching thing, please?
Matching, basically you just collect all those edges which are not sharing any common vertex. For example, here E6 and E3 share a common vertex, which is 3, right?
Yeah.
E5 and E7 also share a common vertex 3. So in a matching set, we cannot take E5 and E7 together. So if I'll
Okay.
take E5, then I want to construct a matching, then I should ignore E7. E7, also E7, E6 and E3.
Okay.
All three I should ignore if I want to construct a matching which has E5, right?
Okay.
So that's the meaning of matching. Okay, fine. Now, after matching, there is called a perfect matching. Okay, so just take. So perfect matching is nothing but a matching which cover the whole graph, which cover the all, sorry, not graph, all the vertices. What does that mean? So that means that I will select some edges from a graph in such a way that every vertex should be an endpoint of at least one of the element in the matching. Okay, so what does I mean? Suppose this is my graph. Okay, suppose this is my graph. I have 1, 2, 3, 4, 5, right? 5 vertices. So I want to find a perfect matching. So does there exist a perfect matching in this sense? So the answer is no, because this vertex, this one vertex is shared by this 3 edges, these 4 edges, right? So if I'll consider E1 in my matching set M, I'm not able to take any of them, right? So there is only possibility to take is E4. So the vertex which has covered by M are basically E1 is covering uh, 1 and 2, and E4 is covering 5. So this is not a good example for perfect matching. Okay, so perfect matching is just a matching which will cover the whole vertices. Okay, just let's try to build a perfect matching in this graph. Okay, so for example, in this graph, if I'll consider my matching M to be, again, there may possible perfect matching, or I mean, it is not always the case that we can able to find a perfect matching. Okay, or basically you can take other simple example. Suppose this is your graph, the very simple example, the 1 by 1 graph. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And these are E1, E2, E3, E4, E5. E6, E7, E8, E9. Okay. Suppose this is my graph G. Okay. And I will consider my matching set M to be E1, E2, E3, E4, E5. Then you can observe, if you take any two vertices or any vertex, suppose I'll take 1, then 1 is the endpoint of E1, right? Similarly, if I'll take 4, then 4 will be the endpoint of E4. Similarly, if I take 8, then 8 will be an endpoint of E3. So that means these edges are covering all the vertices. That's I mean, that's the main concept of perfect matching. I mean, perfect matching is just the collection of all those edges which will cover all the vertices at their endpoints. You guys got what do you mean by perfect matching? Basically, it is a matching in which every vertex should be an endpoint of at least one of the edge. So I'll just write it down. Yeah.
That means again, if we take all the edges.
No,
then
that's
also,
the catch here. Because in matching, we cannot take all the edges. Because in a matching, any two edges should not share the common point. Huh? So
okay.
so that's why I mean perfect matching need not exist always.
Okay.
That's the thing. So perfect matching is a matching which can take or what else I want to say. A perfect matching is basically a matching which cover all the vertices as endpoints, or you can say endpoint, or what they call the nodes. Fine, the endpoint of at least one of the edge. Then that type of matching is called perfect matching. So perfect matching need not always exist. Okay, need not exist in every graph.
Ma'am, not at least, right? At most.
Yeah, I mean, you can say at most, because at most will also contain zero thing now. So the vertices as the endpoint of n edge.
Of an edge.
Yeah, because at most also have zero contained in it.
Mm-hmm. Mm-hmm.
So that's a concept of a perfect matching. You don't have to worry about perfect matching that much. So mainly, main thing is that vertex cover and independent set is main. Main focus here, because they have some properties which we need. Okay. So this is a perfect matching.
Ma'am, can you go to the example that you drew first for matching?
Yeah, this
That one?
this graph G. This
Yeah,
does not have any matching. I mean, any perfect matching.
why, ma'am? Because
If I'll consider,
one will
yeah.
cover 2, 3, 4, and 5. All
No.
vertices.
In a matching, I have to take edge now, right? Suppose if I'll take
Right.
this edge E2,
Okay.
then I cannot take E1, E3, E4,
Right. Right. So
E5,
those
right?
okay. Okay.
Yeah. So the only left choice is E4. So if I'll take this to be my matching, then the only vertices which have been covered are 1, 3, and this 1, this 3, and this 2, and
2
this 4.
and 5. 4 is left out.
We always leave a vertex. So in this graph, there is no perfect matching.
Okay. Got it.
Yeah. Fine.
And so, do the matching exist always for any graph?
Matching always exists, because matching is just a subset. You take a single edge, that will be your matching, right? Because a single edge cannot share any other vertex with. I mean, there is no two edges, so how can they share a vertex? I mean, for sharing, you need another person, right? So if I'll take a single edge as my subset, then that single edge is always a match. So matching always exists. Perfect matching need not exist. That's the thing. For example, this is your matching, right? This is matching,
Right.
but it is not a perfect matching.
So what if we consider just 3 vertex without any edge, that graph? So
Yeah, that graph also have, I mean, there is no edge. So the empty
so
set
can
itself.
we so can we say that phi is the matching?
I think you can, because trivially there is no edge. So trivially there is no concept of matching. So yeah, you can say there is an edge. There is a matching. So matching always exists. So
Oh yeah, because we are taking just a subset of edge.
yeah,
So
we
phi
are just
is the
taking a
subset.
subset.
Yeah.
Phi is also subset of phi.
Yeah, okay.
And ma'am, in a perfect matching, can it contain all the edges?
No, I mean, it depends. For
No.
example, if I'll remove these edges, then if I'll take all the edges, then what are the edges in the graph? Simply E1, E2, E3, E4, right? And this is the whole set E. So here E itself is a perfect matching. It need not to be, it is not always the case that E will it will make a matching, and secondly it will make a perfect matching. There are some examples where all the three sets align. I mean, matching, perfect matching, and edge set. Okay. So there are possibility where the whole set could be a matching and could be a perfect matching. That's what I'm saying.
Yes.
So, You haven't covered BFS, DFS till now. Okay. So you guys watched the BFS, DFS lecture video?
Yeah, ma'am. BFS I have watched, but DFS not. DFS.
Everyone, or I don't
No,
think
ma'am.
it's too
No.
early now. Fine. So there are two processes basically, BFS and DFS. Okay. So these are mainly used for reachability concept. Reachability concept, I mean, you can travel from one vertex to another vertex or not, right? So that's the main motive for constructing BFS and DFS. So these are just process. I will explain how does this work. Okay. So BFS process start step by step. Okay. BFS work step by step. And using the queue structure. Queue structure, I'll explain everything. Okay. For example, consider this graph. So suppose I have this graph and I want to apply BFS in this graph. Okay. So in BFS, there are, so I'll explain, let's try. Fine. So first we'll write what are the vertices. Then there is a called visited vertex or not visited vertex. Visited or not visited parents. You haven't watched at all, no? So I have to start with. Okay. So in BFS, DFS, what we'll do, we'll start a vertex. We'll start with a vertex. Then we'll go to its neighbors, right? And then we will try to explore the neighbors of the neighbors of vertex. For example, from 1, I'll first go to 4. And from 4, I'll explore what is the neighbors of 4. And then 4, the neighbor of 4 is 3. So then I'll go to 3 and then explore what is the neighbor of 3 itself and all things. These are known as BFS. But so in BFS, what we'll do, so first we will write down our vertices. Then we'll take the command visited or not, visited vertices or not. And then we have a column for Q. So Q is basically a structure in which every entry will process using the rule that first in, first out. First in, first out. I mean, whatever thing I'll input first, that thing I have to process first. And for example, in a queue, I mean, if you stand in a queue, whatever person standing, before you will get the thing before you, right? So that's the concept, first in, first out. And this is our BFS, breadth first search. Okay. So here I have 10 vertices, right? So I'll list it down 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So now my goal is to find is there any path between a vertex 10 to a vertex 6. Okay. So that's my goal. I want to find is there any path between the vertex 10 to vertex 6. I mean, in the simpler graph, you can easily tell, okay, there is a path. But when you work with, okay. But when you work with more general graphs, it is always not the case that you will able to find a path. So that's why we build a step-by-step process. So that will help us in the more general or more complicated graphs. Okay. So Q is basically a space where we can put our entries one by one and which will process first in, first out. Okay. So what I'll do, so initially when we have to start our process, every vertex should be labeled by false. Okay. False means that these vertex are not visited till it. Okay. When we visit this vertex, what do I mean by visit? I mean, by visiting means I'll go to that vertex. I'll explore what are the neighbors of that vertex. That's basically the visit thing means. Okay. So first I will start by 10. So now I am visiting 10. So the column of 10 will become the true for now. Okay. So I'll start with 10. So what are the neighbors of 10? So only 3 is the neighbor of 10. So I'll write it down this 3 in my queue that I'm observing. First I'm observing 10. So but I'll take 10 here and observe that 3 is the neighbor of 10. So I'll remove 10 from my queue. I'll write it down 3. Okay. Then since it has only one neighbor, so I'll again start, or again I will visit 3. So if I'm visiting 3, I will remove it from my queue and I will mark this thing to be true in my visited column, right? Okay. So now I will explore what is the vertices, what are the neighbors of 3. So 4 and 2 are the neighbors of 3. So I'll list it down 4 and 2 here. Then also I
Also
have
9.
9.
Oh yeah, 9 also, sorry. Yeah. So I'll list this thing into my queue, but there could be, I mean, you can list anyway, but I'm using the order, decreasing order. Okay. Then I'll also take it to be true. Then I have to visit. Now, here's the thing that in a queue, you will use first in, first out, right? So, but in this level, I entered in this manner. So that's why I'll take 2 first. You can take 4 first also. So I'll now visit 2. So as I'm visiting 2, I'll remove it from my queue and I will take it to be true, right? Okay. That's the basic process. I mean, now you observe what are the neighbors of 2. So 3 is already been visited. I mean, 10 is already been visited. 3 is visited. So what
Ma'am,
are the
one question.
neighbors? 1, 5 and 8 and 7, right? 1, 5,
So,
8 and 7.
ma'am, for
Yeah.
3 visited, why we do not consider 10? Because 10 was already visited.
Yeah, 10 was already visited. That's why we are not considering 10. Okay. So now the new members are 1, 5, 8, and 7. So I will put these entries in my queue. So they are 1, 5, 8, and 7. Yeah.
But the neighbors for the okay, sorry, yeah.
Yeah, right. The neighbors of 2 are 1, 5, 8, and 7, right? Okay. So I am
Yes, ma'am.
visited. So I have visited 2. I'll write down their neighbors in my queue and I also take it to be true, right? Okay. Now, what is the next member in our queue? So queue says first in, first out. So these members are coming after we have entered 4, 9, right? So now I will process 4. So I'll visit 4. I'll list down its neighbors. So its neighbors are 1, but 1 is already listed because of it is a neighbor of 2. So I'm leaving it. Okay. So and 3 is already listed. So 4 doesn't give anything new. So 4 is also visited. So I'll remove it from my queue and I also take it to be true. Okay. Now similarly, next thing I'll visit, what is the next member is 9. Okay. So I'll visit 9. So 9 gives me nothing because 3 is already visited, right? So that's 9 is also not giving me anything. So I'll say that, okay, this is also visited. It's nothing giving me new. So my queue will remain same and I'll erase it. I'll erase my 9 from the queue. Okay. Now the next member for visit is 1. So as I visit 1, the 4 and 2 are already been visited. So 1 is also not giving anything new. So I'll take it to be true and I also remove it from my queue. Okay. Now again I'll visit, what do you say, 5. So now 5 give me vertex 6 and 7 and 8, right? But 7 is already listed. So I'm not considering 7, and 8 is already listed. So I'm not considering 8 itself. So I'll just consider 6 and I'll add it to my queue. Okay. So and I mark 5 to be true. Then again I will visit and also remove from my queue. Okay, so I'll visit 8. So 8 again won't give me anything new because 2 and 7 are already been listed. I mean 7 is listed and 2 is visited. So this won't give me anything new. So again I'll take it to be true, remove it from my queue. Now the next member is 7. So 7 also won't give me anything new. So I'll take it to be true and remove it from the queue. Okay, and at the end I will visit 6. Okay, so 6 also won't give anything. So my queue is empty and my all members are all visited. So this is a process called BFS. Okay, you will go step by step. First, you will go one vertex, just list out their neighbors, then one by one explore its neighbors. For example, I will go to 10, list its neighbor 3, then I go to 3, list its neighbors, then explore it one by one, list them neighbors in a queue, and then explore it. So this is a long process called BFS. It is generally used because it is step by step manner. You can code it into computer. That's why BFS is very important, right? Okay, you got what does BFS does, how it works?
What does BFS stand for?
It's called breadth first search.
Okay, breakfast.
Yeah. There are two things, breadth first search, depth first search. So BFS work step by step, level by level. You can observe first we are visiting 10, then 3, then 2, then 4, then 9. I can do it in this manner also. Go to 3, go to 2, then go to 5, then go to 6. But BFS doesn't do that. BFS observe level by level. What do you mean by level? Simply this thing. First, I'll observe this level. Then I go to this level. Then I go to this level, whatever this is. Then I go to this level. Then I go to this. So something you can observe that it is doing level by level stuff. Okay. This is called BFS. Yeah.
Ma'am, so the final will be 10, 3, 2, like that way, from which we started and visited. The final.
Yeah. Started and visited. Sorry, what is your
What's the
question?
outcome, ma'am? What's the outcome of BFS?
BFS's outcome is that okay, fine. The all vertices are visited, so that means it is possible to move from any vertex to any vertex. That's the main goal of BFS. Okay, so if suppose the process will end, suppose I don't have any vertex, any other vertex to go, right? Because suppose my queue is already empty. Now my queue is empty. Suppose okay, for sake of generality, let's suppose this edge is not there, right? Okay, you can assume that, right? So when I visit, what do you say? When I visit 5, where's 5? When I visit 5, I'm not able to take 6 here because because there is no edge between 5 and 6. So 6 is not a neighbor of 5. So then this 6 will always be not visited, right? So BFS at the end tell that, okay, your 6 is not visited. So that means there is no path between 10 to 6 or between any vertex to that vertex 6. That's BFS does to us.
Okay, so one uses the visited column, whether it is true or false.
Yeah, it
Does
is true or false.
And does Q give also any meaning? Like if it's
Yeah, so
empty
Q will tell us when your process will end. Q tell us your process will end when your queue gets empty. That's the thing. So
so
whenever my queue
that's
will get empty, I'll stop my BFS.
so Q is just the iterator
Yeah,
for getting the visited true or false.
yeah, and getting the flavor of level by level thing. I mean, I'll work with first in first out concept. I mean, I won't jump between the vertices. For example, if there is 4, 2, 3, and 9 is listed here, first I will work with 4, then will with 2, then with 1, then with 3, and then with 9. I won't jump between the vertices. That first I'll explore 9 and then go to 2. This is not possible in BFS. In BFS will do things step by step. First go to 4, then go to 3, then go to 2, then go to 3, then go to 9. Okay.
Sure, ma'am.
And
And so
ma'am,
BFS will always have a starting point, and then
Yeah, the
finding.
starting point is our own goal. I mean, I take it to be 10. You can take some another thing and you can list out your BFS in some other way, right? So the
Got it.
starting point is voluntary, you can say. You can take anything. Yeah, someone saying something?
yes, ma'am, that if it is given that if I have to start from 10 and find the BFS, so the outcome will be like that, no, 10, 3, 2, 4, 9.
No. You won't. I mean, they won't ask you to do this thing. They just simply ask that using the BFS, can you able to find a path between 10 to 6 or not? They won't ask this whole process. This process is just for your understanding, right?
Actually, in CT, it was like that, but I don't, I did it in another way, so that's why I was.
Yeah, it is possible because what happened here, when I go to 3, there are 3 neighbors, right? When I go to 3, there are 3 neighbors, 4, 2, 9. It is possible that someone process 9 first, then 2, then 4. Then its BFS will go in some other direction. But at the end, I'll go to one more thing, okay? So in BFS, this is one general process. Then there is called the parent thing. Uh, parent thing. Parent of a vertex, right? So parent of a vertex is basically those vertex I say to be a parent of J if J is coming from I. For example, here this this 1 is coming from 2, right? First I will visit 2, then I will get 1. So the 2 is called the parent of 1. So in BFS, we also take an account of parent and we also take an account of level. What do you mean by level? Level means in how many how many things I have to tell. First, for example, using the 10, I got 3, right? So 3 will get at the level 1. And from using 3, I got 2 and 4. So 2 and 4 will be at level 2. So these are the things, levels and parents also accounted in BFS, which also gives some information to us. Okay. Yeah. What you guys are saying? Someone is saying something?
Ma'am, if 6 has other nodes, right?
Hmm.
If 5 and 6 are not connected and 6 has other nodes, and all of them will not be covered, right?
Yeah, all of them will be not be covered because there is no path from jumping this component to
5 to
other.
6, and then and it
Yeah,
depends on the starting point. If you started
yeah,
on some point on the other side,
hmm.
then this whole set of these points which started from 10 will not be covered.
Yeah, correct.
Okay.
Whatever you were saying was correct because that's the thing. I mean, your initial point matters eventually. Okay, so okay. So in BFS, we also take account of two things. First is called the parent and second is called the level. So parent is a vertex. We say that I is a parent of J if J is coming from I, right? For example, here our 1 is coming from 2. So we say that 2 is a parent of 1. So let's take another example for doing this parent and level thing. Okay. So again, we are done vertex. Then my true or false, visited, not visited, right? Visited, then parent, and then level. Okay, and then here's my queue. And this I'm taking simple example. Okay, so 1, 2, 3, 4, 5, 6, 8. Okay, so this is my simple graph of vertices consisting vertices 1, 2, 3, 4, 5, 6, 7, and 8. Okay, initially all are not visited, right? Because I haven't started my BFS. Okay, so and parents levels, all things are, and initially all the levels are -1. Initially we'll take that all the vertices are at -1 levels. Okay. Okay, so
Ma'am, what is level?
level is basically we'll assign a number in which what can you say, at which part, I mean first level, second level, in which step you are going through that vertex, right? I mean how many vertices, by passing those vertices you can able to connect that vertex. That's basically called a level. I'll explain. Okay, let's start. So initially all the levels are -1. So you guys say what in at which vertex we should start. Okay, so should we start from 1, 8 or any other vertex, whatever you want to?
4.
Okay, you want to start from 4. Okay, fine. So let's start our BFS from 4. Okay, so for 4, initially my queue is empty. I'm visiting 4 now. Okay, so I'm visiting 4, so I'll write down what are the neighbors of 4s. So the neighbors of 4s are 2, right? So now I'll update the information here that I'm visiting 4s. I'll mark it to be true. And the parent of 4 is nothing because 4 is independent, right? Okay, this level thing. And whenever we go to another level, we'll add 1 to the level. Okay, so since we have started from 4, we'll add it 1 here, so it becomes 0 basically. So 4 is at level 0, right? And I'll enter 2 in my queue because 2 is getting from 4. So that's why 2 is coming from 4, so the parent of 2 is 4. Now you got it, what is the parent level thing we are updating and how, in which sense we are updating. Now there's this here.
Ma'am, it is depth first search, no?
No, this is breadth first search. Breadth first search will take account parents level. In depth first search, we have pre number, post number, right? In breadth first search, we have queue, parent, and level thing. Okay. So now we have visited 4. We account 2, and I'll enter 2 in my queue. So what is our next member? So next member for visited 2, right? Okay. So if I visit 2, what are the neighbors of 2? So they are just 1 and 5. So I'll remove 2 from my queue since I have visited, and I'll enter 1 and 5 in my queue. I will also take here to be true, and I will update the level of 2 to be 1. Right? Because 4 is at 0 level, 2 is at 1 level. You guys getting what we are doing with levels?
Yes, ma'am. Incrementing as we go through. Right?
Yeah. So 0, 1 level. Now we have 1 and 5. So I will visit 1. But now 1 and 5 both will have at second level because they are getting at the second level and they are coming from 2. So that's why we update the level of 1 to be 2 and also the level of 5 to be 2. And since they are coming from 2, I will add parent of 1 to be 2 and the parent of 5 to be 2. Right? Now I'll visit 1. So as I visit 1, I'll get a neighbor 3. So since I have visited 1, so I'll remove it. I'll update 3 here. I'll take 2 here. And I'm getting 3. So I will add the level of 3 to be third level because I'm getting 3 to on the third level, right? Because it is a third thing we are getting. Okay, fine. So the level of 3 is now missed. Yes. So this is level of 3. So level of 3 is 3. Okay. Now the next thing I have to visit is 5. So I have to visit 5. So I'll take again the neighbors, which are 2 is already visited. So I'll take 8. So 8 is there. 5 is gone. I'll take 5 to be 2. And I will update the parent of 8 to be 5 because 8 is coming from 5. And the level of 5 to be 3 itself, not 4. Okay. So the level of 8 is 3 itself, not 4, because they are coming from the level 2 things, 5 and 4. Since 1 and 5 are coming from level 2, so that's why the level of 8 is 3. Are you getting, guys, or this is a little bit confusing?
Yes.
Okay. I think I missed.
So, ma'am, can we say the level will always be the level of the parent?
No, the level of the number is the 1 plus the level of parent. For example, 8 has parent 5 and 5 has level 2, right? So
Okay,
the
plus
level of
1.
8 is 3. So it is 1 plus parent. That's
Always, right?
Yeah,
Means as a
always.
rule. Okay.
So now I already
It's,
visited.
is the
Yeah.
level is dependent on the path also? Like
Yeah,
in this
no,
graph?
because we are taking level. I mean, I'm listing, for example, 1 and 5 I will get at the, I mean, what can you say, at the neighbors of 2. So that's why I listed 1 and 2 as the same level, 2, 2, right? I haven't listed 2, 3. So level doesn't depend on path. Okay. It depends on, it depends basically on parent, from which parent the vertex is coming from, right? Okay. Now we have to visit 3. So 3 will give us 6 and 7. So I'll write it down 6 and 7 in my queue. I will remove 3 from my queue and I will list it to be true. And what is the, we have missed the parent of 2. No, parent of 3 is 1, right? Because it is coming from 1. and the level of 3 is 3, correct? So now what is the parent of 6 and 7 is also 3, and the level of 6 and 7 will add up accordingly, but the level of 6 and 7 will be 4, right? Now you guys getting, right, how we updating the level?
Yes, yes.
Yes, ma'am. Yep.
Okay. So 6 and 7 also listed. Now I'll visit 8. So 8 will, yeah, 8 is the last thing. I mean, 8 will give 5 and 6, which is already visited. It won't give me anything else. So I'll remove it. And 8 is coming from 6, right? So I have already updated 8. Okay, 8 is coming from 5. It is nothing giving me. So I think we have listed all the parents itself, right?
But ma'am, for 8, your level will be conflicting then, right?
No, no, no. The level will be itself only. I mean, the level won't change. Level will change for neighbors, whatever you get. For example, when I visit 3, I will get 6 and 7. So then I update the level of 6 and 7, not the level of 3. Because the level of 3 is already been updated. That's the
So
thing.
what will be the parent of 8? 5 or 6?
Parent of 8 is already 5 because we get 8 from 5, right? This is your 8 and this is your 5. We get 8 from 5. When we visit 5, we get 8. So the
Okay, so
parent
wherever
of
the first
8
time
is,
it is getting, that will become the parent.
yeah,
It
yeah, that
depends
will be
on the
counted.
starting.
Because
Okay.
the visiting will depend on Q, right? But the parent and the level won't depend on Q. Right?
Thank you. Yep.
Fine. So this is BFS. Just practice it out because it will take time to remember how we are going through from one level to another level. So there is one good example done in the video lectures itself. Now you guys know what is the BFS. So try to solve it by yourself and try to write down the parents and level only. Okay.
Ma'am, we can do it by any one method, na?
What do you mean by any method?
Like not by like the in the previous example, you don't tell it's about levels and
Yeah. In previous example, I just tell what is the BFS. In here, I am also accounting what is the parent and level itself, both of the things. Because parent and level will give some kind of shortest path between the vertex. So that's why they are important. Okay. So I think we'll discuss in the next lecture because we don't have time now. So I'll suggest this go through one or two examples using the BFS. Just try to list it out parents and levels. Then you can able to understand what is BFS and DFS. So I'll go through DFS because DFS says some other things also. I mean, it is more rapid than BFS. In BFS, what are we doing? We are some sort of doing repeated thing, right? First I'll go to 5, then I'll go to next thing, then I'll go to next thing. DFS don't do that. DFS we just cover using the whatever, randomly. For example, in BFS, what I'm going, so first I will start from 10, then go to 3, then I'll visit what are the vertices of 4 and 2 also. So then for using 4 and 2, I'll go to 1, then I'll go to 5, 7 and 8, then at the end I'll go to 6. That is the BFS doing. BFS do the things level by level, but in DFS what we'll do, in DFS we'll start from 10, go to 3, go to 2, go to 5 and then go to 6. We don't do we don't require the other business. That's the difference between BFS and DFS. But DFS also have some other details. So I'll explain it in the next lecture. So you guys just try to make yourself handy with BFS. What does BFS do and how we listed our parents and levels. Okay. So that much I think you can do now. Any doubt in any doubt? Regarding parent level thing, you guys understood, right?
Yeah, ma'am. How this will be used in a problem, means real life problem?
Yeah, that in real life problem, there are so many. For example, if you want to connect, you guys go to online exams, right? So there you have so many servers and all. So each server will connect to some what you can say, a primary server which will handle all the servers, right? So there we need minimum number of computers which can take cover of all those things, right? So ultimately we want to find such a places where we can put our primary computers or primary things which will cover the whole thing. It just minimize our conditions. You're getting?
So it's always about the
Huh.
path, shortest
Yeah,
path.
it's always
Okay.
about a path,
Okay.
neighbors, and connectedness. These are the main things. So in some sense, you want to find the shortest path between any two vertex. So BFS will give it to you. In next lecture, we will describe what do you mean by a tree. So BFS always give a spanning tree, which is a main concept, which is again an important concept in graph theory because it is used at several places, I can say.
Okay.
Yeah,
And
networking is one of the examples.
on the neighbors, ma'am, can you help with little more? So edges is always about the path. About the neighbors, it helps in knowing more properties about neighbors, or
Uh,
it is just about the edges only, where all it can connect.
no, what's your question? I'm not getting.
No, no. The question is there are two components, right? One is your vertices and another is your
Uh,
edges, right? Your
mhm.
path is always your edge,
Yeah,
right? Which edge will connect, right? But
yeah,
neighbors is all about vertices, right?
yeah, yeah.
So
Because
in neighbor, yeah, sorry.
yeah. Just say what are you saying?
Yeah, so vertices. So in neighbors, what more we can find is because with neighbors also we are trying to find path only, right? But anything more about neighbors, it can be asked like how many points it is connected.
Yeah. Actually, that is called the degree of a vertex. So that's
Okay.
also I have to describe.
Oh,
Basically,
okay.
degree related to a vertex is basically the number of neighbors it is connected. So degree of a vertex V is, you can say, that number of vertices, but it is not described in this way. That degree of a vertex is number of edges which is connected to that vertex. That thing we called it to be a degree. Okay, not the number of, but ultimately it is the same thing, right? Because
Mm-hmm.
that suppose I have five edges, so that means there are five vertices connected to the vertex, right? That's basically number of the edges connected to V.
Ma'am,
It's
but it will be
called,
always one less than if there are four vertices, then there will be three edges.
yeah, it's always less than that. Yeah, number of edges, number of vertices, degree, all things I will describe in the next lecture. Okay, because we
Okay.
have to
Sure.
go through trees also. What are the possible, what is the maximum number of edges in a graph, minimum number of edges in a graph? That whole thing we'll describe in next lecture. Okay,
Sure,
because
ma'am. Thank you.
it's
Mhm.
you guys have just don't leave. I'll share the PDF. Okay, you guys have any other doubt? Any doubt regarding?
Yeah, ma'am. And what will be the weightage in term of these? Means 9 to 12 week will be of higher weightage in term, or it will be
9 to
equal
12.
across all 12 weeks will have equal distribution in the final term.
I think they will have equal distribution. I'm not sure about that, but I'll let you know. Okay, because
Okay.
I think they will have the equal distribution. I will let you in the next lecture because I am not sure till now what are the
Sure,
weightage
ma'am.
of.
Thank you. Yep.
Is there any technical issue or any language error in the question paper? Or you guys face some difficulty for understanding any question?
Not now. Till then, everything is clear.
That 11th, 12th question was confusing to me, ma'am, in the quiz.
Okay, what
Uh,
is it?
where we had to find one to one,
Uh,
that one, where we had a modulo, right? Where we had
uh, yeah.
that one, I I did the first one correct. The
Hmm.
second one was really confusing to me. I
Okay,
wasted a
so
lot of time on that.
okay. Fine, I'll check. You want me to discuss now?
No, no, ma'am. No, ma'am. That's already discussed in Arpit sir's class.
Okay.
Yet I have
Ma'am,
doubts for that, but I have to review it first.
Yeah. Yes.
ma'am, I have a doubt. Can I share it?
Yeah, sure. Just go to BFS once again and try to make levels and parent things comfortable first. Then go to next things. And just watch the lecture. I think sir have explained it well. What is the process? What are the main goals to explain that process?
Ma'am, I shared it.
Yeah, got it. This one.
Ma'am, I got it. I got the right answer, but I have like I couldn't follow that lectures properly because I have some exam. So I wanted like I was getting the two solutions for that. So ma'am, the right answer was one. So how to like check for it like the right answer? It will be one.
How do you get two solutions? I mean, it's
Ma'am,
9
ma'am, I just a second.
versus.
Ma'am, I have taken the 3 square x and then plus 3x minus 6 is equal to 0. So I consider 3 to the power of x as a.
Yeah,
Then
right.
then it will be a square plus a minus 6.
Yeah.
Then so that will be like I have to calculate the roots. So it will be a square that it will be a square plus 3a minus 2a.
Yeah, right.
So it was like 3a minus 2a, then it will be a minus 3 and a 2. A is equal to 2.
Yeah, a is equals to 3 and a is equals to 2, right?
So
Then
I thought that there is one negative sign, so I opted only one solution. But I'm not confirmed for that. Like I just did it in a random way. Like, but I want ma'am like if the approach was correct for that solution.
yeah, whatever approach you have used, this was correct. But okay, the screen is visible, right?
Yeah, ma'am.
Question is 9 to the power 3, 9 to the power x plus 3 to the power x minus 6 is equals to 0, right? But you have done that 3 to the power x square plus 3 to the power x minus 6 is equals to 0. So you will let this to be k, right? So it's k square plus k minus 6 is equals to 0. So this will become k minus 2, k minus 3, right? That this much you have done, right?
Ma'am, k plus 2 and k minus 3.
Oh, k plus 2 and k minus 3. So this is
One
k
will be
is equals to,
negative. Like one will be negative.
yeah, sorry. This will be plus, this will be minus, then multiplication will be 6, addition will plus. Yeah. So k is equals to 2 and k is equals to minus 3, right? So I think I have discussed this thing already, but let me think, right? So now this is your first thing to do, that find out the, I mean, first reduce into the polynomial and then go for the roots, and then you have to find an x. Now your goal is to find an x1 and x2 such that your 3 to the power x1 is equals to 2 and your 3 to the power x2 is equals to minus 3, right? So you can find an x1 such that 3 to the power x1 is equals to 2, right? Because the graph of 3 to the power x1 is I mean, this is a graph of 3 to the power x, right? So if you want your value to be 2, suppose 2, so there will always exist an x1 such that 3 to the power x1 is equals to 2, right? This much you know, right?
Yes, ma'am.
But for this part, observe, you want an x2 belongs to real number such that 3 to the power x2 is equals to minus 3. But this is not possible, right? because you can observe the graph. This is a graph of 3 to the power x, and this is your minus 3. You can never, I mean, you cannot find such an x2 for which 3 to the power x2 is equals to minus 3, because this thing does not belong into range of 3 to the power x, right? Minus 3 ultimately does not belongs into range of 3 to the power x. So here you are not able to get any x2. So that's why it has only one solution.
So, ma'am, in these type of questions, I have to always ignore that negative values when it comes.
No, it depends on a function.
Okay. It
You
was
should
an
consider, I mean,
exponential.
you just have to take that, okay, this negative value can be belong to the range of function or not. If it is belonging to the range of function, then it may be a solution. Okay, so that's the thing.
Ma'am, actually, like for the week 6 lecture, I'm finding it very difficult, ma'am, for these type of questions. Like when they come to like find the number of solutions.
Mm-hmm.
Like both
Yeah.
my answers were correct in the paper, but I'm not very confident for these type of questions. Actually, I couldn't saw like lectures properly also because I had my exam like OPP2, OPP1. Well, what
Okay.
should do I should do now?
I mean, there is no way. I mean, you first have to get the concept that why we are saying that this is a root. That's the reason now why we are saying that x2 is a root. So if I put x2 here, I will get 3 to the power x2 to be minus 3. And if I'll put minus 3 in my equation, I will get a 0. So in some sense, I mean, you just understand the concept. There is no shortcut. What can I say? So just try to do it. If not, that's also fine. I mean, there will always be a one or two topic which we are not comfortable also. So it's okay. If you are not getting, I mean, just try by yourself. If you are not getting, then it's fine. Don't be stressed out about these things. Okay. You got my point. I mean,
Yes,
are
ma'am.
you? Yeah, I know it is tough of finding the number. First of the thing, they should mention what number of distinct solution and all things. That are one thing that we should take care of. But yeah, finding number of solution will take little time. I mean, little practice actually.
Ma'am, I was trying in doing the before quiz too also, but I was getting stuck. So I was like pretty sure that I will do the wrong answers. But
Don't, I mean, just don't put this. I mean, just try to argue logically now that why it cannot be a solution, right? If you try to argue logically, then you will be confident that okay, this cannot belong to the range, so it cannot be the solution,
yes,
right?
ma'am. Yes, ma'am.
Yeah.
Just one more question, ma'am, please.
Yeah.
Share it.
Ma'am, in the meantime, one quick question. Will
Yeah.
there be another session, ma'am, for the week 10?
Since we haven't covered the whole theory, so I think yes.
And would that be tomorrow?
Uh, that I'm not sure, but I'll let you know because we have to do DFS and that tree things. That what do you mean by a tree, spanning tree, degree of a vertex? So that thing required half an hour. So I think whoever will take next session, he will recall DFS and spanning tree, or what do you mean by a tree in a graph, acyclic group and all, acyclic graph and all things. Okay.
Okay.
Yeah, this solution. So here you will get, I guess, x is equals to 0 is the one solution. Uh, right?
Yeah, ma'am. It only one solution. Yeah.
Yeah,
I,
only one solution, x is equals to 0. So what is your doubt? I mean,
ma'am, can you give a solution for this?
okay. So you just have to process with the same thing. I mean, let me solve. Okay. So what is the question? ln of 7 plus ln of 2 minus 4x square is equals to, is this
ln of 14.
ln of 14?
Yeah, ma'am. Yeah.
Okay. So it is pretty, okay, fine. So here you just apply the property of log that this will become 7 of 2 minus 4x square and this will become ln of 14. Just take exponential on both of the sides. So this will become e to the power this thing is equals to e to the power this thing. So it will become 7 of 2 minus 4x square is equals to 14. So this will implies 14 minus 28x square is equals to 14. So it got cancelled out. So this will implies x square is equals to 0. So it will imply x is equals to 0. So here you don't have to go through that polynomial thing. You could just use the property of log, take the exponential from both sides to cancel out the ln and then work it out.
Ma'am, I have always seen that we are multiplying first here rather than sending this 7 on the other side and dividing by 7, right? Meaning dividing whole by 7.
Yeah,
Why
you
are we
can do both of
multiplying?
them. I mean,
I'm confused because that is easier, right? That is easier number to deal with. But I have always seen
yeah.
whoever is solving it, they're multiplying and then canceling out 14. So I'm just wondering why.
I mean, multiplication is simpler than division. I mean, now suppose this is 14. Okay, fine. Suppose this
Right.
is 16, then it is
Right.
some
Right.
16 by
In
7.
that case, yeah, it will become some number over there. But in
Yeah.
this case, looking at it, I would just divide both the sides by 7 and then I would just deal with 2 and 4.
Yeah, you can do it too. It's
Thanks.
fine. It's good to observe. So you got Bhumika how to
Yeah,
deal with
ma'am.
it.
Yes, ma'am.
Yeah, it's not always the case that you have to go through the polynomial method. You can observe the basic properties of log and all things and then work. These type of question require little bit practice. I mean, it's not always the straightforward strike.
Thank you, ma'am.
Yeah. Okay. Okay, so shall we end this session here? Any other doubt, query, anything?
Yeah, ma'am, one last thing.
Yeah.
As we have seen so far, though, so the number of as they ask the number of solutions, find the number of solutions. So we have to only find the distinct number of solutions always.
Yeah, always.
Because I've been
You
victim
have
of
did
this.
the wrong thing, right?
Yes, sir.
Uh,
I've been victim of this.
but actually, they should
I have
mention
marked
distinct
two.
solution. Okay,
Yeah.
they should mention. That's
Yeah.
there's a catch. So I'll also tell the people that yeah, we should mention distinct solution. But there was like, okay, it is understandable that we are asking distinct solution. So I said, okay, fine.
Yeah. So I
Because in
think
some,
this concept is come from the roots and zeros from the polynomials.
LinkedIn or mail address for career guidance. I don't have a career. How could I give you?
Sorry.
Okay, fine. I'll try to do LinkedIn. So you guys are doing this only one math one course or also doing stat one?
No, ma'am. I have
All four,
selected
ma'am.
the three.
Ma'am,
Okay.
Python.
Python also.
Hello, ma'am.
Yeah.
Ma'am, where I can get a solution PDF for quiz 2? Is there any
Solution.
PDF there?
I don't know actually. I mean, will they provide solution PDF for quizzes?
Don't know, ma'am. I didn't get anything, but I want one to check whether what I have done wrong in the questions.
Okay, okay. So I'll try to put some solution PDF in the portal. Okay. So I'll ask
Yes,
them.
ma'am.
Yeah.
Ma'am, yeah, ma'am, I have the same issue, ma'am. Actually, what I've done, I'm not sure that whether the process is right or wrong. So,
Yeah.
if the solution is there, it will be very helpful, ma'am.
Yeah. So I'll tell them to put a solution PDF.
Ma'am, I just got joined late
Yeah.
this session. Is there tree explained in this session or in the next section?
Tree explain. I mean, we will explain in the next session because tree
Okay,
is
okay.
important concept. So
Cyclic, acyclic?
yeah, cyclic, acyclic, DAS, all things.
Okay, ma'am. Okay.
Directed acyclic graph, and then topological sorting also we have to discuss.
Okay.
So, yeah, we'll discuss. So I'm on LinkedIn by my name Samiksha Lonkar. If someone wants, they can share my request. But I won't use LinkedIn so much. Use. So, okay, so we'll end this session. Okay. Good night, everyone. You can leave now.
Yes, ma'am. Good night.